Okay, so what we're going to do now, I'm going to go over review problems that might help you for the test, and maybe homework if they are sufficiently close to problems on the test. So the test, it'll be of similar format to the last one, 5 problems, hour and 15 minutes, and bonus problems. 2 questions from chapter 4, 2 questions from chapter 5, 1 question from chapter 6, which the question from chapter 6 would basically look like a quiz. I'm just going to give you a system of equations and ask you questions about it. You know, is it competitive, is it not, justify, you know, draw the phase plot, draw the diagram for the solution curve, things of that nature. So tomorrow, I usually don't like teaching after a test, but tomorrow I probably will. So buy energy drinks or coffee or whatever you have to keep your brain going after the test. Because chapter 7 is actually a pretty long chapter. I'd rather start it sooner than later. It's a lot. Chapter 7, it's not difficult stuff, but it's just a lot of stuff to throw at you. It's basically starting with statistics, and as you can see here in the bonus problem for the quiz, I asked you a little bit about statistics. If you remember, what is mean and mode and median and quartile, so things like that might come on the bonus problem. I might ask you about histograms on the bonus problem, things like that. Setting up a frequency table, things of that nature. So that's just a heads up for testing. Now, are there any questions that you need? Yes. Which one? Oh, we'll do the whole thing. Why not do the whole thing? Okay, so this is from fall 2008, problem 3. It is one of the ones from chapter 4. So you're given a differential equation, y dt equals 5 minus y plus 3, minus 1, right? And it says to graph the graph of g versus y, sketch the solution curves if your initial condition is y of 0 equals 3, show concavity and the y value of inflection points, also do stability analysis, blah, 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 right? Basically, it tells you all the things that I showed you how to do anyway when we were doing the problems in chapter 4. So if you just mindlessly follow what we've been doing in class, you'll automatically do all of these things anyway. So let us begin. We basically want to perform qualitative analysis on this problem, right? How do we do it? What's the first step? Steady states. How do we find those? Set this equal to 0. So it's 5 minus y, y plus 3, y minus 1 equal to 0. This means that y is equal to 5 or minus 3 or 1. Right? So that is, these are your steady states. What's the next? We need the inflections next. How do we get to the inflection points? Let's find the derivative of this. Now, how do we do that?
Expand it.
You could expand it. Let's expand it. So this is G. You could also do the product rule. There are several ways. I'm not sure which one is going to be easiest here. Let's just. So if I expand these two, what do I get? Right? You get 5y plus 15 minus y squared minus 3y, all that times y minus 1. Alright, so this is 5y minus 3y, it's just 2y, so I get minus y squared plus 2y plus 15 times y minus 1. You can expand again, take the y, multiply everyone in here, I get minus y cubed plus 2y squared plus 15y. Take minus 1, multiply everyone here, I'm going to get plus y squared minus 2y minus 15. Simplify that a little bit, add minus y cubed, 3y squared, 15 minus 2, 13y. So I did the y cubes, the y squareds, the y's, and we just have minus 15. So now we find the derivative, which is
negative 3y squared.
Minus 3y squared plus 6y plus 13. Right? And now we try to find this equal to 0 for the inflection point. Right? So how do we solve that? It doesn't factor? So you'd use the quadratic formula if it doesn't factor. It's annoying when that happens, but as you can see, nasty problems like that happen from time to time. Are you sure this doesn't factor?
Can't be take a 3 out, can you?
No, the 13.
is it?
3 doesn't factor? No, let's see. So your y would be minus b plus or minus the square root of b squared minus 4 times a times c all over 2a, which is minus 3. And what is this under that, under the division sign?
You're going to get negative 6 plus square root of 192
192? Okay.
over negative 6.
So square root of 192 is what? Well, I mean, you have a calculator, so you could just give me the approximations.
So you're going to get negative 1.309 and
1.309
Yes,
or
and positive 3.309.
3.309, right? Roughly speaking. So those would be your inflections. So you found the steady states and inflections. What's the next thing?
Draw the graph for the first derivative.
You need the stability diagram. As it's called, it's just the graph of the first derivative. So we are going to graph y prime versus y. Right, so what are our equations here? There's a minus 3, there's a 1, there's a 5. Right, so these are our steady states. There's 3 of them that we're going to have to test. Figure out what's going on. I can plug in a minus 4 into that equation, see if it's above or below. So if I plug in a minus 4 here, this is positive times negative times negative. So I know it's positive. And it's going to be a cubic. I know if I plug in something like this, so I plug in a minus 4, I get a positive. Plug in something like 0, I'll get negative. Plug in something like 2, I'll get a positive. Plug in something like 6, I'll get a negative. Right, you test these points, and then you can draw the graph. And so we have ours in, well, I didn't really draw this correctly. The dip should be somewhere over here. Right, there's an inflection point roughly at minus 1.3. That's where we're going to have our inflection point. There's another one at positive 3.3. What?
It wouldn't be at negative 1?
What's at negative
The
1?
dip, like the bottom. No.
Negative 1.3. Yeah. Now, how do we test these steady states?
It's positive or negative.
Oh, right.
How do we test this one?
It's the right.
Over here?
Yeah.
It's going to the right,
Left.
left. What about this one?
Left.
Left,
Right.
right,
Right.
right,
Left.
left. This is
Smiley.
smiley face, stable. This is
Sad.
sad face, we're unstable. This is
Smiley.
smiley face. So that was the stability diagram. Technically that's in part D of the question, but whatever. Yeah, so after that, 3 we usually skip. That's where we talk about concavity with that G prime times G thing. I don't particularly care if you show it or not, so you can skip it. Only show it if you're not sure, but based on what we've been doing, you should be sure at this point. And the final graph, the solution graph, which is what part B tells, sketch the solution for y of 0 equals 3. So we're going to put in all our points, our steady states.
-3, 1, 5.
So -3. This is a steady state. 1. This is a steady state. 5. This is a steady state. Inflection points were -1.3. -1.3. That's an inflection point. And 3.3. That's an inflection point, right? So we show all of these guys, right? And we want to begin at 3. Right? So y of 0 equals 3 is where we want to start. And what would happen? Are we increasing or decreasing?
Increasing.
Increasing, right? If I'm at 3, the arrow is telling me I should be going up towards 5, right? 5 is going to be a stable, steady state. I'm heading towards there. What's my concavity here?
Concave up.
Concave up. I have to be like a smiley face so that when I hit this point, which is an inflection, I can switch the concave down so I can level off. And that would be your solution. Any questions? So this one was sort of really nasty because of, finding the inflection point was really annoying in this problem. From time to time they give ones like that, not always, but sometimes, But never forget the process, right? Steady states and inflections, stability diagram, then solution diagram, right? Always the same process. And even if they might label the questions differently, you just write this down and you can label it differently yourself. Just say, this is my answer to part D, this is my answer to part B. Just sometimes they'll ask you things out of order to try to confuse you, and then you try to do this before that. Oh my God. Don't let it fool you, right? Just go through the steps. Basically, this is the method that we learned from chapter 4. Any questions on this? Yes. Steady states override inflection points. From time to time, it will happen that you get a steady state here and an inflection point is the same thing. Assume it's a steady state. Steady states are bigger. They override inflection points. Because steady states is where your derivative is 0, which means your curve would level off anyway. You wouldn't pass that. Because when you hit it, you would go to 0. Yes?
Can we go over number 8? Just fall 2008.
In the same fall 2008? Problem 8. Right, so this is actually very similar to a question we had on test 1. Your daughter needs to be able to draw $50,000 a year from her college savings fund that you started at birth to pay for college expenses and obtain a medical degree. Assume that she will take 4 years for a bachelor's, 4 years for medical, then an additional 2 years for residency, and yearly spending will be consistent from year to year. She's spending $50,000, we're assuming, every year. At the start of her college career, she intends to invest her savings in government securities that should return 5.5% per year, compounded continuously. A, obtain an equation for dp dt where you don't know what P naught is, you don't know the initial amount she has to invest. Find the general solution. P is going to be the balance in her balance in the government securities account. Right? So, okay, how do we set that up? Part A. What is dp dt?
0.255p.
Right. first you have to remember this is actually a harvesting model. Right? Compounding continuously means it grows proportional to its size, but she's deducting a certain amount of money per unit time. R in this case is going to be the interest rate. H is going to be the fixed value that you are deducting per unit time. So this is dp dt equals, the interest rate was 5.5%, written as a decimal. Is this minus 50,000? Your P of 0 is P naught. We don't know how much yet we have to invest in order to have this thing work out in our favor. I think that is all we have for part A. Right, so part A is just to say this, basically. Right? But you have to realize that this is what's going on. And obtain the equation, find the general solution. So part A actually asks us to find the solution as well. How do you find the solution to this?
Take out the
Separation of variables, right? So I can factor out a 0.055. This would be P, 50,000 divided by this is what?
909.
9?
909090.
909090.
9.
0.90. I have enough 9 zeros?
Yeah.
3 sets of 9 zeros? Okay. So 2 decimal places. The other one be 9090. It repeats forever. So this would end up being a 1. We'd round that out. Talk about money. Next step would be
DP.
separate the variables. Bring the t's over there, bring the p's over here. Divide the whole thing by this. So we have dp over 909090.91 equals 0.055 dt. Going to integrate both sides. Here I have ln equals, this is 0.055t plus c. And raise both sides to the exponential. I get p equals c e to the 0.055t plus 9090. Now the question says we have to solve it for the general solution with the yet unknown value of P0, which means it's not good enough to have a C here. I need my answer to have P0 in it, P naught. So all I do is just apply that initial condition, pretend P naught was a number and just apply it that way. So what I do is, since P0 equals P naught. This means when T is 0, my P value is this. I'm not sure what that value is at the moment, but I'm just going to plug it in. Plug in T equals 0, and plug in P equals P naught. And so this would mean C is equal to P naught minus 9090.91. Which means finally my P is equal to and that's our solution, the general solution. Questions on this? In part B, we said how large must the initial savings be so that she can continue drawing 50,000 until she becomes a doctor. So what do we need to happen in part B?
Time.
Time to be what?
10.
10 years.
10. Takes 4 years for a bachelor's, 4 years for a medical degree, and 2 more for a residency. Therefore, we want P of 10 to be 0, right? So she starts off with some amount of money in the account. She's going to be drawing it for 10 years. At the end, you want nothing to be left. You want just enough for her to withdraw for her education. And you spent 50,000 a year on her already. Just like, you don't want any more, right? Just after 10 years, that's it. You're on your own now. Okay, so you want P of 10 to be equal to 0, but this is what P is, so you just plug in T equals 10, plug in this equals 0, and you solve for that. So 0 would be equal to P0 minus e to the point 0.055 times 10. Means this, I'm going to bring this over, that gives me minus 9090 minus 0.91. You divide that by e to the point 0.55, and then I'm going to add this. Right, I just solved this. I subtracted this, move it over, then divide by this, move that over, then I added this to move it over, and that's what I'm going to end up with. And that would be roughly what?
It would be 184,591.
184,000?
384,591 and 8 cents.
8 cents. Yeah. So for her to be able to do this, you put that amount of money in a bank account earning 5.5% interest, and she'll be good until she graduates from residency.
Her daddy's got money.
Yeah?
Can we go to fall 2010 number 6?
Is this going to be that much exam number 2?
Yeah.
Is it that?
Fall 2010 or fall?
I have it.
Fall 2010.
It's actually a problem from our homework.
Yeah,
Yeah.
which is on
Really?
the final too.
Yeah. I don't remember which problem.
Fall
One of our
2010.
homework problems.
Problem 2.
It was,
Problem 3.
Problem 3.
Problem 7. 7 and number 10, right?
yeah, it's the matching of the pictures. I
Oh,
think it's the,
number 6.
yeah.
6, yeah.
The final is 12
Yeah.
problem and 10.
I don't think you have to worry about things like that really, but not for the test anyway.
Is that an option level or is that what
Not as optional.
Like, I'm not going to put a problem like that on the test. I can just explain to you really quickly what it's about, and maybe.
it's just that's not that, you know.
Yeah.
That's not that bad.
This week.
Follow
Basically, the idea is the graph on the bottom tells you what the x and y are doing separately, and then you sort of use that to figure out what's going on the top. So, for example, if you have place plot C, I'm just taking out a random example here where we have this thing going on. Right? And you have to match that with one of the graphs on the bottom. Which one looks like that's what it's doing? You would sort of have to notice what is happening to your, you'd have to from this figure out what's going on with x, and then figure out what's going on with y, and you sort of piece them together. And here you sort of examine direction. So if this is your initial, what actually happens to your x value? Only looking at the horizontal, what actually happens, right? You're at this point, you decreased to the left, and then you started to increase to the right, right? So if you had to draw a picture of what x is doing, what would it be doing? Well, it'll decrease a little bit, then increase, right? That's what x would be doing. Just by looking at this, you realize start here, you go to the left, and then you go to the right. It means your x value decreased, and then it started increasing. This would be sort of a picture of what your x would look like. And then you sort of, well, what would happen to the y? what's going on with the y. If I plot y versus t, or x versus t, what would the difference be? Well, what's happening to the y value? It's just increasing, right? From the beginning, all your y values are higher. So the y value is just going to be a graph that goes like that. And then you sort of pick which one of these graphs have something that looks like that. Well, this one. So the answer to that one would be, there's a graph that looks like this, and then this, right? Where that's the y and that's the x. That would be the one that you match with this. It's basically just dissecting what the x is doing different from what the y is doing. You sort of look at it that way. If you have something like that circle, right? And then you sort of figure out, what is the x doing? You know, what is the y doing, right? What's happening with your x? Increase, then decrease, then increase, then decrease. Your x should be doing that, right? What's happening with the y? It's going up, then down, then up, then down, then up. So the y would be doing the same thing. So it's matching up with one of these. Now you sort of figure out, which one of these would the circle be? Well, it's going around the same path all the time. So it stands to reason the one that have sort of this constant height of bumps, right? If the bumps start getting smaller, you start to go in a spiral, right? So then this one would match with that one, right? So it's just a matter of looking at what's going on in the left and right direction, separate from what's going on in the vertical direction, and sort of dissecting them, and then you sort of match it up. That's sort of the idea, but it's that's not on my test, and it's not very likely to be on another final. This was. It hasn't been on a final since this one. Yeah. Yeah, what's the... Spring 13, number 6. So yeah, if you get this, that's great. If you don't get it, don't worry about it too much. That's what you said, right? Spring 13, number 6. So this is a chapter 6 problem. So we have 1 dt equals 0.02 and 1. We have that system of equations. And by the way, this is sort of standard how they ask the question. It'll always sort of look something like this. So they'll say an ecosystem of 2 species is modeled by this system of differential equations. N1 and N2 denotes the number of members of each species, and the rates are as follows. Find the steady state solution of the system, determine which are stable. It will be helpful to graph the null times, which we already know how to do. When the populations are 30 and 40, determine whether each population is increasing, decreasing, and what rate. Okay, so.
Will it always be a linear no plan on the plan?
Yeah, they always do that.
I know.
So let's just,
Good year.
if we go through our process, we'll be able to do this, right? So they never ask you if it's competitive or not. Sometimes they do. But we can still do our method and see what we should expect later on. So, is it competitive or not?
No.
It's not.
No.
How do we know?
And
Low
one
value.
by
So-
Lowe's method.
Where does the arrowhead go on this one?
Bottom right.
Down. This one.
Bottom left.
So what does that mean here? And 1 is going to survive, right? So it's not competitive, and 1 should win. So you sort of know what's going to happen. It's going to make sense to you that N2 should be decreasing, right? You notice that the last question asks you, do they increase or decrease? It sort of makes sense. N2 will decrease. If you start at 40 or 30, he's going to go to 0 eventually. So let's actually see if we care about that. So we know what's going to happen. Let's actually find the steady state. How do we find those?
And 1 is 0.
Set these equal to 0. In the first situation, we have two cases, and 1 equals 0, or this equals 0. Which means LCD of 60 and 90. Hmm? 180. So then you multiply this through by 180 just to get rid of the fractions. 60 goes into 180 how many times? 3 times.
2.
This goes into it 2 times. Now we can sort of solve for n1. n1 would be equal to 180 minus 2 and 2 over 3. So now in 2, so we got this from 1. In 2, how does this affect things? If I plug in n1 equals 0 in here, then
And 2 is 0.
then we get n2 equals 0, or 1 minus n2 over 80 equals 0, which means n2 equals 0, or n2 equals 80. And so you get the steady states 0, 0. You also get the steady state 0, 80. Then you do the second case. If n1 is actually equal to 180 minus 3 and 2 over 3, then what would we get? I would plug this in. I would have n2 equals 0, or 1 minus n2 over 80 minus n1. I'm going to plug this in. 180 minus 3 n2 over 3 over 40.
Times 80.
And so now we have to solve this, right?
80.
You can multiply by 80. You'll still have this. This is a 2. You'll still have a fraction though. You have to multiply by 80 times 3 basically. This is really 1 minus 180 minus 2 and 2 over 3/4, 12. Right, so that's sort of what you want to multiply by. Find the LCD of those two. LCD of those are?
3.
Yeah.
240.
From here.
I thought it was F1 was 180.
Yeah, that was a typo that I continued here. It's supposed to be a 2. I'm getting it from here. I solved for it before. And I'm just plugging it in. And then we
240.
have to go and solve this whole equation. So that's the annoying part of this. You can multiply by what? 240. 80 into 240 goes how many times?
3.
80, 120 to 240 goes 2 times, so it goes 2 times 180 minus 2 and 2 equals 0. This is 240 minus 3 and 2. 2 times 180
360.
plus 4 and 2. So I have 3 and 2 plus 4 and 2, that's just n2.
120.
240 minus 360 is
120.
120. It will be minus 120 and I move it over here, right? So it's 120. So in this case, if n2 is 0, my n1 would be plugging 0 here, 180 over 3, which is just 60. So I get the steady state 60, 0. Here, if n2 is actually 120 and I plug it in here, n1 would be equal to 180 minus
-20.
2 times, what?
This 20.
What?
Oh, nothing. She think.
Okay, plug in 2 times 120, I get 240. over 3.
So 60 over negative 60.
That's negative 60 over 3, which is negative 20. And so the steady state for this one is minus 20, comma
120.
120. Right? Obviously not a realistic steady state for population, but that's what we get. And with that, we can sort of draw a diagram. N1 should. So now we draw the null climbs, right? So what do we look for? Look at these guys here in brackets. The guys in brackets, you set them equal to 0 and you plot them, right? So you look at this one and you go like, what if N2 is 0? N1 would be 60. N1 would be 60. And then you say, what if N1 is 0?
90.
And then N2 would be 90. And right? And then you connect those two. Right? That is the N1 null climb. Then you do the same for the second one. What if N2 is 0? N1 would be 40. And then you're like, what if N1 is 0 and 2 would be 80? And then you connect those guys. Now it's going to intersect somewhere over here in the negatives. It's going to intersect somewhere at negative 20, comma 120, right? But we actually don't even care about that because it's not even realistic for us. The right side is this. This is N2 null point. So if I take this, I move over here, what happens? N1 switches to the right. If I move over here, what happens?
It's goes to the right place.
Those are the arrows. I don't really care about over there. It's not even realistic. So, yeah, we have all this now. It says you might want to be helpful discussion on all kinds. We did, and we did that stability diagram. Now it says, suppose you start with N1 equals 30 and N2 equals 40. So N1 equals 30, N2 equals 40. I assume that will be in this region.
30 and 40?
Yeah, it'll be somewhere in here. You can always test, but I'm
30.
pretty sure it's going to be over.
Yeah, I have it in
Yeah,
the inside.
inside here.
You think it's going to be inside?
But I have like squares, red paper. It's in the inside.
It's
Oh.
on the inside.
It's supposed to be in here?
I think so. Yeah.
Okay, so
But then
I mean, you can always check in your calculator just to be sure. Right? All you have to do is plug in 30 and 40 into, we're looking at the N2 null time. Plug in 30 and 40 into here. If you're N1, which one is 30 and which one is 40? N1, if I plug in 30 here, and I plug in 40 here, do I get a positive or a negative? Right?
1 minus half.
Plug in 40 here, this is just 1 minus a half, which will give you a half. Minus 3/4 gives you negative, so you should be on the negative side of this line. You should be over here. So that's going to be 40, that's going to be 30. And then, now they ask you, what's happening? Each population is decreasing, and at what rate? Well, what would happen here to each population? What would you do? What would the solution graph look like?
Increase past the line, then decrease.
It will go up, increase till you pass here, and then starts to decrease to hit there, because we actually did the test and we know where it's going to end up. It's going to end up when N1 survives. But at this moment, what's going on? each is increasing, right? You're moving to the right and up. Both N1 and N2 are increasing at this moment. And then if you want to find out at what position, so to answer part B from the phase plot, we see increasing, and the rates are you would pretty much just plug the I erase it. You would pretty much just plug them in. Let's see here. 6.02 times N1, we have 30 times 30 over 60 minus 40 over 90. And then for this one, we plug this in. This is N2, we actually plug in 40. N1, N2 is 40 over 80. And N1 is 30 over 40. We plug it in to determine whether you plug it increase or decreasing and at what rate. Let's see. So you compute this, but we saw that one of these were negative, right?
Yeah.
This one was negative?
Yeah.
So he should actually be decreasing.
Yeah, because it's inside the thing.
Negative. The negative side, did I mix up the lines?
No, we got it right.
No, it's not.
N1 survives.
It's what it is,
This point should actually be over here.
yeah.
Yeah, that would make sense, yeah. We're in the wrong region. So this one was actually negative, but the question, they actually want you to find the answer. Just put it in your calculator. You'll get negative something, and you plug this into your calculator, and you should get positive something. So from the phase plot, we see, and you can actually double check this, N1 is increasing, which makes sense. This is 1 minus a half minus 4/9. N1 is increasing, and N2 is decreasing. So yeah, correct. That spot where we were originally was in the wrong position. Which is a case in point. It goes to show that, you know, if you make a mistake, it's possible to catch yourself. Sometimes I see in tests students like make mistakes, and I'm like, the thing you did over here totally contradicts what you did before. You should have known that, oh, something's amiss. Go back and check something. You know? Yeah.
Can you explain again that?
How we found this point? Well, first, the real way to do it is to figure out what value the line itself gives you. And then when you plug in the point, what value that gives you, and see who's bigger or smaller into those equations. Yeah. And see who gives you the bigger value when you plug them in. So you can sort of plug in, you know, if you plug in we're looking at N2 is the line that we really wanted to focus on, right? If you plug in N1 equals 30 into that line, I erased the original. Plug in N1 equals 30, you can see that the overall graph, whether it would be how big the number would be if you plug this in. And then you sort of see what values the line itself gives you. So you plug in 30 and 40, you get a number, and then you pretty much want to figure out, since you know the equation of this line, you'll know what points are on that thing. When N1 equals 30, what is N2? You solve for it. Let me write it out. Can I get rid of this? So let's say where should the point? So now what do we have? The situation we have was the following. This was an N2, that was an N1, and we want to know where does 30, 40 end up. So we're looking at the N2 line because that's the one that we're really close to. In the N2 line, the null line for N2 was 1 minus N2 over 80 minus N1 over 40 equals 0, right? So that's the line we're looking at. Now, if you plug in N1 equals 30, then that would give you 1 minus N2 over 80 minus 3/4. And so this would give you, N2 would be 1 minus 3/4 times 80. So this would be 1/4 times 80, which would be 20, right? So you go here, and you know that when you plug in 30 here, the value for this line gives you is 20. But now they said it's 30, 40, so you know that you'd have to go above this line to hit that 40. Right? So you're just plugging in the values and seeing where you get. Right? And if you made the wrong assumption here, you could have caught your mistake when you're doing this, and you're like, oh, it says it's supposed to be decreasing according to this, and then you're like, oh, maybe. And then you try this check, right? You just plug in the numbers, and you're like, oh, well, the y value I should get is 20, but they give me a y value of 40, so I have to actually be above the line.
Could you go number 3 from
Same year, number 3.
2013.
Looks like a nice one, 2013. Let's start it here.
Based on the cellular top, right? It's not the problem is that the last one, I want to like say.
So find the steady state solutions, the inflection points, and sketch the curves for y of 0 equals minus 1, y of 0 equals 0, y of 0 equals 1, y of 0 equals 5, and y of 0 equals 8. So basically qualitative methods on that graph, on that differential equation. What's the first thing we do?
Steady states.
Steady states. So this means y squared 7 minus y equals 0. So we have y equals 0 or y equals 7. Those are your steady states. And we also want to find inflection points. So our g here is, I just multiply out 7y squared minus y cubed. So g prime is equal to 14y minus 3y squared, which which means
0.
14y minus 3y squared equals 0 for inflection points. Is for IP. And so we can factor out a y. So you get y equals 0 or y equals 14 over 3. These you call your inflection points. Right? So here's a situation where steady state and inflection point overlap. How do you deal with that? Think of it as a steady state rather than an inflection point. And what's the next step? Stability diagram. So we are going to graph y versus y prime. And we see this is a cubic. We have two steady states, 0 and 7. The 0 one is squared, it's multiplicity 2, so you know it looks like a y squared at that point. But you can test values. If you plug in a number between 0 and 7, like 1, plug in, that's positive. Plug in 1 here, that's positive, so you know the graph is above. Plug in something over here like minus 1. That's positive, you know the graph is still above. Plug in something bigger than 7, like 8. This is positive, this is negative, so you know the graph is below. And so your graph should look like and test the steady state on the left side, what happens?
Right.
Or to the right,
Yeah. All right.
to the right,
To the right,
still to the right,
to the left.
to the left. What does that tell you about this one?
Stable.
Stable. Tell you about this one?
Medium stable.
Semi-stable. Right? And then
So chapter also put the inflection point.
yeah, so this one is sort of both a steady state and inflection point, but for our purposes, we always think of it as a steady state. This is a steady state. The other inflection point would be here, which is 14 over 3. Step 3 we skip, do it only if we have to. And 4 is going to be where we are putting in our solution curves. Y versus t. So our steady state, 0 is one of our steady states. So right on this, right on the horizontal axis is the steady state. Seven is the other steady state. Inflection points, 14 over 3. Somewhere up there. Inflection point. 14 over 3 is roughly what? 4 point something, right? Because 15 over 3 is roughly 5, so you know it's 4 point something. You can plug it into your calculator too if you're not sure. So that sort of gives you some context for where these guys should be. So now let's start with the first one. If I start at minus 1, what should I be doing? Right. From our stability graph, we see the arrows pointing to the right. If I'm at minus 1, I'm moving towards 0, and it's a steady state. What's my concavity?
Concave down.
Concave down, like a frown, so I can level off. Right? The next one is, what if I'm actually at 0? What's going to happen? I'm just going to stay at 0. Right? Because at that point, my derivative is 0. I'm not growing. I'm just horizontal, straight line. What if I am at 1, which is going to be over here?
Concave.
That's a little inflection point.
Right, it's going to be increased towards 7 because all the arrows are pointing to the right. So I'm increasing, And I want to be concave up like a cup and then down like a frown to level off. 5 would be slightly bigger. What's happening at 5?
Concave down.
Down like a frown. 8.
Concave down.
And where am I going?
Concave to the 7.
I'm going towards the 7, because then when I'm above 7, the arrow points to the left. I'm supposed to go towards 7, so concave up like a cup. And so those would be your solution. Questions on that? Yeah, so I'm going to give you a couple questions like that one, basically. How about spring 2014?
Page number 4
Oh,
in there.
on what?
Spring 2014.
On 2014?
Yeah.
I just went to 2014.
I'll put 2013.
Number 4 is not in our thing.
Oh.
Who number?
You just spring 2009.
I just want to start off number 3 as well. Just want to see what you guys do with it.
Which exam is that?
The spring 14. Number 3. It's the same thing we just did, except this is equal. That's a 5. That's a 5. So if we're doing step 1 and want to find the steady states here, how do you find the steady states? It's equal to 0. How do you solve that?
Y's gotta be 1 or 0.
Huh?
Yeah, you can do
What?
Y out
Five
first and then
or
factor. Yeah.
You multiply out first and then factor?
Yeah.
Yeah.
Right. So I can multiply both sides by a -1 if I wanted to. And then sort of factor 5 and 1 minus. Yeah, so y would be 1 or y would be 5. I just wanted to point out that one because I've seen people tackle this in incorrect ways in the past, so I just wanted to. Some people would like move the 5 over here and then y equals 5 or this equals 5 or do crazy things like that. That's not, it's not correct. Okay, just want to make sure you have your algebra skills honed. Okay, what was the next question?
Spring 2009.
You get to see this.
Spring 2009, number 10. And number 3. Yeah, number 3 is a harvesting model. So you can write down a differential equation for that. And if the initial number goes well, using qualitative method. So yeah, it's a harvesting model. It'll just be a straight line. We did that one already. Number 10, they sort of gave you the phase portrait and they wanted to Number 10 has a slight tricking. So based on the phase plot, by the way, what do you sort of think about this situation? How do you describe that population? It's competitive, right? What makes you think that?
It's going to the both stable, very unstable state.
Because where it ends up depends on where you start, right? Sometimes N1 will win, sometimes N2 will win. So it's a competitive system. Now, let's actually look at this and see what happens. Spring 09, number 10. Find the steady state solutions, blah, 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 and then based on the diagram, how we characterize the stability of each steady state solution. So these two are semi-stable, all the other steady states are unstable, and it's a competitive system, basically is what we'd say for part B. But what tells you it's competitive? How would you figure that out?
You could just do
The letter numbers are.
Okay, so let's say I did the arrow. What's for this one? What about this one?
that tells you that it's competitive.
Because it's 3 100s versus 1 100, right?
But that's not.
Oh, yeah.
300 should be bigger, so
Yeah.
it goes up.
Right, that's how you're gonna see it. There's a trick here. The trick is they threw a 3 in here, right? You have to notice that. It doesn't look exactly like our form. You basically have to write it. This equation, you'd have to think of it or rewrite it as 1 minus n2 over 100 minus, this 3 you have to put under the bottom. It's actually 100 over 3 in the denominator. So it turns out that this one has the smaller denominator when you put it in standard form, so the arrow has to go here. Right? So if you weren't careful and you missed that 3, you're like, oh, they're the same, who's bigger? Does that mean competitive? And no, the 3 here is what's going to save you. You put it in the denominator, it becomes 100 over 3. So the denominator of this one is really 33.333, and that gives you the depends case, which tells you, oh, it's competitive. Right? So, yeah. I had some students complain to me in the tutoring center about this. Low's method doesn't work. It's the 3. Just notice there was a 3 there. Yeah. Right, so that one is due. Right, so when it says characterize instability, notice that the stable steady states are either this one. Let's talk about that. Let me talk about that.
Can you do the stability diagram, the graph, rather like the old school method for that?
Old school method.
Like with the 1 and the 2 and then.
We could. I mean, we can cheat here and see what the steady states are. One is going to be 100, 0, right? And one's going to be the origin, one's going to be some point in the middle. The other one's going to be 0, 100. And all right, so let's actually draw these graphs. What does this one look like? If n2 equals 0, n1 is 100, we already plot that. If n1 is 0, n2 would be 50. So your first null time would look like that. And then in the second case, if n2 is 0, n1 would be 100 over 3. And so it's going to be a third of this. It's going to be like here, 100 over 3. And if n1 is 0, n2 is just 100, which is here. This. Right? This is going to be the intersection point, whatever that is. We're not finding it at the moment, but I know that this is going to happen over here. This was n1 nullifying. This was n2 nullifying, which means if I jump over here, what happens?
Arrow goes to the right.
Down.
The guy that was to the left is now to the right, over
Up,
here.
right.
It goes up and to the right.
Up and to the right. If I go over here,
Up to the left.
up and to the left. So this sort of tells you, if I start like close to up here, all these points are going to go down and then up. Right? And if I start like over here, all these points are going to go down and then that way. Right? Which is why the diagram looks like that here. Right? If you actually did it the old school way and drew in these things, you'd realize, oh, that's what's happening. If I start down here, they're all going to go to N1, while if I start up here, they're all going to go to N2. So that says this guy here, semi-stable. Right? If you're close enough here, you'll go towards it, but otherwise you go away from it. Right? This one here is also semi-stable. You don't go to it from both directions. This one, the origin is of course unstable, because you're always moving away from the origin, and this one is also unstable. Right? Because whether you're above or below, you're running away from it. Right? That's how we define stability, if you want to go towards it or not. Right? So yeah, in part C, it's definitely competitive. Right? You can justify it with Lowe's method, or just look at this diagram. It says sometimes N2 will win, sometimes N1 will win. It depends where you start. That is the characteristic of a competitive system. So yeah, so like I said, 5 problems. 2 of them are like chapter 4 stuff, 2 of them are chapter 5 stuff, and 1 of them is like this, and then there are bonuses.
Could you fall from 10?
Which one?
I think it's hard. Fall from 10, number 2.
Number 3.
It's hard.
Okay, so dead leaves pile up on the ground under force at a rate of 3 grams per square centimeter per year. At the same time, 75% of the accumulated leaves decompose in a continuous process each year. Write the differential equation for your year. So let's call it something. P equals the number of leaves, or the amount of leaves. How do I want to say it? Quantity of leaves. So now you want to write a differential equation, dp dt. Now what's going on, right? There's a continual process of accumulated leaves decomposing, right? It decreases by 75% continuously, right? Which means whatever amount of leaves are currently under the ground, we will have 75% less of them per unit time. Right? So it's decreasing by that rate. And then it says, you know, from the trees, the leaves are falling, you're actually adding to the amount now by 3. So that would be the differential equation. Okay, let's see how this is worded. Dead leaves pile up, so the trees are adding to it, so it's a harvesting model where the dead leaves falling from the trees add to the accumulation. 75% leaves decompose. So yeah, so then that's part A, part B. Assuming the initial state with no leaves, so we're assuming that P of 0 is 0. Use qualitative methods to determine the long state. Right, so then we have to draw pictures, right? So we're doing, we can do the stability graph. This is just a straight line. This would be increasing, decreasing. This would be a stable, steady state. What is the steady state? Well, you set this equal to 0 and you solve for P. P would be
3 over 0.75.
3 over 0.75, right? And that's going to be what?
4.
That's 4. And so 4 is where the steady state will happen. And then you go to your solution graph. Right, this is P versus P prime. And this is P versus T. Here's 0. Your steady state is at 4. And it's a stable steady state, so if you start at 0 accumulation of leads, right, what would happen?
Concave down.
Concave down, going up towards 4. So that's what would happen. Yeah, so your rate of decrease, you can think of sort of like an interest rate, how that thing is growing. And then the trees are adding to that. That's like a harvesting where you're introducing new members to the system. Yeah, that one you have to read carefully.
You said one, how many questions from each chapter? One from chapter 4?
2 and 1.
2 from chapter 4, 2 from chapter 5, 1 from chapter 6. Know qualitative methods and know how to verify something by doing quantitative methods. So for example, if you're doing the qualitative method on something and you realize something dies, I'd expect you to be able to tell me when does that happen, right? If you realize it dies, tell me when. And that you can't use pictures to tell you. You'd have to actually compute it. So you also need to know that. Whose is this? I guess we stop there.